Hey everybody, my name is Taylor Sparks. I'm the editor-in-chief at the journal Integrating Materials and Manufacturing Innovation. And I'm here to tell you about a brand new paper accepted in our journal. It's entitled The Importance of Hyperparameter Optimization During Training of Physics-Informed Deep Learning Models. This comes from authors Lenau, Dimiduk, and Niezgoda at Ohio State, Los Alamos, and Blue Court Software. Now, the point of this paper is all about physics-informed neural networks. If you're not familiar with those, essentially what these are is that instead of letting the loss function be any old thing, we're going to put constraints on the loss function so that it better reflects reality, for example, physical equations, okay? And in specific, what they're looking at in this paper is physics-based regularization terms that get added there. Their hypothesis is twofold. First off, adding these physics-based regularization terms should make the models more accurate, be able to train on less data, and they should converge faster. That's their first hypothesis. The second hypothesis they have has to do with this second section shown in yellow here, which is that it probably matters a great deal how you go about doing your hyperparameter tuning. And there's good reason to believe this. In the introduction, they point out lots of the prior art, and there's two articles in particular I want to point to. This one in reference 20. In that paper entitled Rethinking Hyperparameters for Fine-Tuning, they essentially argue that if you take these pre-trained models and use them for scientific tasks, it really matters how you get the hyperparameter tuning right. The second one, which they discuss a little bit down here, talks about the loss function landscape and how it can actually be pretty difficult to learn. This comes from a couple of colleagues actually at the University of Utah, where I'm at. So what did the authors actually do? Well, if you jump down here to the methods section, you see that they're going to generate data. They're going to do it with phase field modeling, and they're going to be modeling spinodal decomposition to generate microstructural images. Then they're going to build a model whose task is to take in an image and predict as an output what the corresponding stress field would be. And they're using pix-to-pix GAN. So what are they going to be comparing then? In the study, they're going to use a baseline neural network and compare that with 3 different physics-informed neural networks that have different physics-based term regularization. The soft constraints that they're going to impose on the loss function have to do with plane stress boundary conditions. And the way that they're going to impose this regularization is through one of 3 methods. They're going to do either simple addition, the math shown here, and essentially what they're going to do here is it biases the generator to synthesize stress fields that are closer to equilibrium. Or they could try it with a sigmoid function. This is now going to be implemented in the discriminator, and they point out that this adds additional probabilities on the discriminator network that will encourage the generator network to produce stress fields that have plausible divergence fields. And then they'll try it again with the inverse tangent approach. This is now going to do essentially a similar thing as the sigmoid function, but it will be implemented on the generator, and it allows us to do a nonlinear comparison of the divergence errors. So what do they find? Well, first off, do things converge faster? Do they converge to be more accurate? They do. They find that when compared with the baseline, these physics-based regularization terms do improve things. You can see that when you actually look at what the target stress fields were for these ones and what the baseline, sigmoid, simple addition, and inverse tangent were able to put out. Maybe it's a little bit easier to see if you actually compare where the errors were showing up here. This is the absolute error of these stress fields from these different models. So what did they actually find? First off, the physics-based regularization does offer an improvement. No surprise there. That's a good sanity check. The second thing that they learned is that the hyperparameter tuning process is essential, and if you do it wrong, your model will not perform well. Third, they found that these physics-informed models did not drastically reduce the amount of data needed. And they found that the additional time for doing the hyperparameter tuning correctly adds enough compute time that this may not be something that's going to save you compute time because you're not getting away with less data and you're spending more time on this, but the end result can be better. And so the applications of these are going to be where physical accuracy is a priority and not compute time and compute resources. So I hope that you'll read this paper and learn more about it. You can find it in the journal Integrating Materials and Manufacturing Innovation. Okay, see you next time.